Okay, this is Mr. Sitta. Working on Chapter 19, Acid Bases. For the worksheet I posted, I'm going to show you how to do a K expression. It's very easy. So if I had an acid like hydrofluoric acid, HF, I react it with water. This is a weak acid. Ks are for all weak acids, okay? It shows how strong they are. If this is an acid, the water is going to act as a base. And so that will donate the H+, and my products will be H3O. Okay, now that is what remains of the base, so that's my conjugate acid. Plus, what's left of the acid is the base of the acid, which is fluoride. Conjugate base. Okay, to do a K expression, in general, Ks are equal to the concentration of your products over the concentration of your reactants to a coefficient, to a power. Okay, the coefficient would be whatever, the power is whatever your coefficient is. Now, you never include water, any liquids or solids. So for me to write a K, here's what I do. K equals, these are my products, H3O and F. It's H3O, then times the F. They're to the first power because the coefficient's 1. And then the bottom, I'm not going to include water. The bottom's just going to be HF. And that is how you do a K. Now that's the K of an acid. Whenever you take water out of something, it's going to have a little subscript that makes it special. This is the K of an A, and it stands for an acid. So that's called an acid dissociation constant. The higher your K, the stronger your acid is. That's more products. A lower K equals a weaker acid. Okay? What that means is if this number is high, that this reaction, this is a two-way reaction. It favors the product, so that's a lot of acid. If this reaction is low, if it's over here, if the K is low, then the H hasn't dissociated much. That's what makes it a weak acid, by not dissociating a lot. If I put in a strong acid like chlorine, there's no double arrow. Chlorine gives 100%. I would end up with everything in the products, and the reactants would go to 0. Well, if you go to 0, it becomes undefined, but a K of a strong acid is almost like going to infinity. If you divide by 0, then it's getting infinitely large. So Ks of strong acids are all infinite. But we don't really use Ks for strong acids. They're really used for weak acids. I'll give you another example of a base. If I was to take fluoride, I'll take the product. Fluoride can only act as a base. I'm going to react it with water, so the water will donate the H to the fluoride, and water will now act as an acid. It's amphoteric. Now the H, the conjugate, becomes HF. That's your conjugate acid, plus OH, conjugate base. Now here's how I define a K for this. It's not hard. It's the two products multiplied by each other. So it's HF with the bracket, which means concentration, times OH. You put brackets around them. The brackets mean concentrations. Divided by the F. The water's not included. Now, since this is a base, we don't call it a KB, a Ka, it's called a B, and that would be a base dissociation constant. And something I can tell you that if you take a Ka and you multiply it by a Kb, it ends up equaling the Kw of water. 1 times 10 to the negative 14th. So there's another little equation that relates Kas and Kbs. As the Ka goes up, the Kb goes down. As the Ka goes down, the Kb goes up. They're inversely proportional. And what this says, it says if you have a weak acid, the weaker the acid, the stronger the conjugate base. The stronger the acid, the weaker your conjugate base. Just the opposite here. The stronger your base, the weaker your conjugate acid. The stronger your base, the weaker your conjugate acid. So a strong base makes a weak conjugate, and a strong acid makes a weak conjugate. I'll do one more. If I had HCO3 and I react that with water, and say my product is H2CO3. If it's H2CO3, then the H went that way. Water acted as an acid. HCO3 was acting as a base. This would be my conjugate acid plus hydroxide, conjugate base. Now, to go backwards, this H would go back to that to get back to the beginning. If I'm going to define a K for that, it's going to be H2CO3, bracket, times hydroxide. It's really easy. Divided by HCO3, and we never put water in it because a liquid is considered to be, it never changes concentration. And I put the -1 there. And this would be the K of a B because it's acting as a base. And that's how you do Ks. Without acid bases, I'm going to just show you one real quick. So if I was to take hydrogen gas, react it with nitrogen gas, and I'm going to produce ammonia. This is a very famous reaction, Haber process. I need 2 N's, so I'm going to put a 2 in front of there. That's 6 H's, so I'm going to put a 3 in front of there. Okay, say they're all gases. I can define a K for this, and the K would be an H3, and I'm putting this one because it has exponents. The exponent goes in as a 2. With acids, you never really get exponents. They're always 1 to 1. The H2 would be to the 3rd power, and the N2 would be to the 1st power. And that would be, we put a little EQ at equilibrium. That's how you write a KEQ if it's not an acid. The coefficients become your exponents. You put them to the powers. And it's always times, not plus. Okay, very good. You can try that out on the worksheet. Do Ks for the acids and see what you get. Probably won't test you on that, but it just wanted to show you the relationship.